Continuity is something we studied in 8th grade. We had the conversation back then that a function is continuous if you can draw it without picking your pen or your pencil off the paper. Clearly, we can see this first one is discontinuous at C. We say that it has a jump discontinuity because this first part comes in and it ends right there. The second part comes over here. 8th graders would say we can't get from here to there. Okay. Using our knowledge of calculus, we would say that the limit as x approaches C from the left is not equal to the limit as x approaches C from the right. That is one reason why a function would fail to be continuous at a point. Well, let's look at another one. We have over here, we have that the limit as x approaches C from the left and the limit as x approaches C from the right. Those are equal to each other. They're approaching the same thing, but we have a hole in the graph. I think we'd probably all agree that the hole in the graph makes the function discontinuous. It's discontinuous, though, because the limit as x approaches C of the function f of x is different from the value of the function at f of C. I have a hole in the graph. I have a point up here. These are not equal to each other. The function is not continuous at that point. The last one, we have a graph that seems to be approaching infinity as we get closer and closer to C. We can find the limit as x approaches C. The limit as x approaches C is positive infinity. However, we cannot find f of C is undefined. That is the reason that this function is going to be discontinuous. We have three examples of discontinuity. We have a jump, we have a hole, we have a vertical asymptote. All three of those fail to be continuous. Where does that take us? It takes us to our process, the template we're going to use for showing that a limit exists. Here comes a little bit of power teaching. My calculus students know that a function is continuous at a point if three conditions are met. First one, the function is defined. There is a point there. The second condition, and you have to have this one in place, the limit exists. The limit from the left are equal to each other. The third condition is that the limit as x approaches C from both sides, that has to exist, and it must equal the value of the point. All three of those must exist in order to state that a function is continuous at a point. Let's actually put this into practice. So here are the four steps. Show that f of x is defined at x equals c. Show that the limit as x approaches c exists. Show that the limit as x approaches c if the function is equal to the value of the function at that point, and state your conclusion. We're going to go through and do it with this example. So here we go. Suppose that the function f of x, piecewise function, is equal to ax squared plus 3 if x is less than 2, and 3x minus 5 if x is greater than or equal to 2. We want to suppose that it is continuous at 2. For what value of a? Find the value of a which will create a continuous function. Well, if this is true, if the function is going to be continuous at 2, the first thing is that f of 2 is defined. Well, what is f of 2? F of 2, we plug it into the bottom piece, is 3 times 2 minus 5, it's equal to 1. Check, it's defined. Second, the limit as x approaches 2 of f of x needs to exist. Well, if it's going to exist, what that means is that the limit as x approaches 2 from the left must be equal to the limit as x approaches 2 from the right. What is the limit as x approaches 2 from the left? Left of 2 means numbers smaller than 2. The function is defined for numbers smaller than 2 to be ax squared plus 3. So we're going to say that as x approaches 2 from the left, that the left side is going to be a times 2 squared plus 3. What's the limit as x approaches 2 from the right? 2 from the right means numbers larger than 2. Numbers larger than 2 satisfy the last condition. We have 3 times 2 minus 5. This is the limit from the left, a times 2 squared plus 3. This is the limit from the right, 3 times 2 minus 5. If the limit is going to exist, we have to be able to say that those are equal to each other. This now becomes the way we're going to figure out a. A times 2 squared is 4. 4 times a plus 3 is supposed to be equal to 3 times 2, which is 6. 6 minus 5 is 1. So if 4a plus 3 equals 1, that means 4a equals negative 2. Divide both sides by 4. A is equal to negative 1/2. So what does that mean? If a is equal to negative 1/2, then these two things are equal. If these two things are equal, that means that the limit on the left and the limit on the right are equal. What does that mean? That means that the limit as x approaches 2 exists. The limit as x approaches 2 of f of x exists, and it is equal to, let's see, 3 times 2 is 6 minus 5 is 1. Check. It's using this second step that in this case allowed us to figure out what a is. In order to finish off the continuity, step 3, we need to state that the limit as x approaches 2 of f of x is actually equal to the function's value at 2. Well, that's true. They were both equal to 1. And so the last is our conclusion. We like to do the 3 dots, which means therefore f is continuous, C-O-N-T-I-N-U-O-U-S, at x equals 2. That is what we were asked to prove. Done. High five your neighbor. That brings us to the intermediate value theorem. The intermediate value theorem is the one that doesn't quite roll off the tongue as nicely as I would like for it to, but I've seen a lot of the students just developing a nice intuitive understanding. The intermediate value theorem states that if f is a continuous function on an interval ab, what do I mean by continuous? It has no holes, no jumps, no breaks, and no vertical asymptotes in between. These are x coordinates, an x1 and an x2. If the function is continuous between these 2 points, and m is some number between f of a, those are y values, then there exists a number c, such that c is between your endpoints, and if I evaluate the function at c, I get m. Let's try that one more time. What are we told? We have a function, f of x. This is f. We have endpoints. We have x equals a, and we have x equals b. My function is continuous inside those two. It might be continuous outside. I don't even care about that. What I know is I have a point on my graph over here and a point on my graph over here. This is the point b comma f of b. This is the point a comma f of a. What the theorem says is if I pick a number that is larger than this y value and smaller than that y value, any number from here to here, any number at all, and that's what they're calling m, then my function, the graph, must cross the line y equals m at least once. One more time. If I have a continuous function on an interval and I pick a y value, if I pick a value in between the y values on the endpoints, then the function must be equal to that value at least once. This is called an existence theorem. An existence theorem means we know that something exists. We don't know where it is. There is no promise of exactly where that value is. Heck, there could even be more than one place. In this example, we have one time that it crosses, 2 times, 3 times. We are guaranteed that it happens once. That's all. Let's see how this is going to show up in a problem, and I think people can feel better. Suppose that f is continuous on the interval 1, 7. That is essential. If you have a function that's not continuous on the interval, can't do it. And data is given in the table below. How many zeros must f have in the interval 1 to 7? Zeros. How many roots? Well, I have these points. I have 1, -3, 3, 4, 6, -2, and 7, 5. How many times must the function be equal to 0 if it's continuous? Some students like to plot the points. Plotting the points is nice if you have the time. Here's 1, -3. Here's 3, 4. Here is 6, -2. Here is the point 7, 5. I can imagine a function that connects those 4 points. Maybe that's the function, maybe not. But I can see that on this interval, I'm going to have a root over here. I'm going to have a root over here. I'm going to have a root over here. Now here's the trick, and this is where you need to be careful. This, although it might be helpful for you to get to the number 3 roots, this is not acceptable as a proof. If this is your evidence, sadly, you're not going to earn any points. So don't do that. Do it if you need to get the picture. But here's what we do. 1, we state f is continuous. How do we know that? Well, it was given. F is continuous. Given. Second, where do we expect there to be a root? We expected a root between these 2 points. Why? Because at f of 1, it's -3. Because at f of 3, the value of the function is equal to 4. We suspect a root in there because the left endpoint is less than 0 and the right endpoint is greater than 0. There must be a root in there. So we'd say, so by the IVT, intermediate value theorem, there exists a root in the interval 1, 3. There, that's 1 root. Where do we expect another root? We expect another root between these 2 points. Same argument. F is continuous. We're given that. Check. Second thing, f of 3 is equal to 4. F of 6 is equal to -2. There must be a root in between, but let's make sure we express it correctly. F of 6 is less than 0, and that is less than f of 3. So, by the IVT, your intermediate value theorem, there exists a root. There exists a root in the interval 3, 6. Unfortunately, I've run out of space, but we would have the same conversation, the same justification over here for why there's a root between the point 6, -2 and 7, 5. That would be an adequate defense of why there must be 3 roots. Part B of this question, is there a value of t such that f of t equals -5 in that interval? Well, is there a t? Are we guaranteed a solution to this? The way we're going to decide is we're going to see, do we have at any of our endpoints an endpoint below -5 and an endpoint above -5? If that happens, then you would have a solution. And that doesn't happen. So we could say no such value exists.